Okay, so good morning and welcome to Classical Mechanics 1. Today is Tuesday, the 6th of September, 2020, and I think this is our 11th meeting. Yeah, so I hope everybody will join us in good time. There were some questions about the fourth assignment, so I think I will simply discuss the problems now. Before I start that, are there any things you would like to say? Okay, if not, I will share my screen. Okay, I think you can see it now. Apologize for this difficulty. So can you hear me and also see my screen?
Yes.
Okay. Yeah, I hope things will go smoothly from here on. So we are considering the punctured three-dimensional Euclidean plane. By punctured, I mean I've removed the origin, and this is a scalar field defined on it. And we are asked to compute its gradient. So by definition, the gradient of psi is partial psi partial x times x hat plus partial psi partial y hat plus partial psi partial z hat. So we simply compute these derivatives. That is easily done. So partial psi partial x is going to be given by x squared plus y squared plus z squared to the power of minus half. So it's going to be minus half minus 1 times minus half. I'm just doing the chain rule of differentiation times 2x. So I presume you have all tried this out. So do stop me if anything is unclear here. Okay. Yeah, so if we simplify this, this is going to be given by minus x upon x squared plus y squared plus z squared to the power of 3 by 2. Okay, are you with me so far?
Yes, sir.
Okay, thank you so much. That was Mayur, if I'm right. Okay, so then we simply combine these. By the way, okay, this is the answer, and then partial psi partial y would be gotten by replacing the x in the numerator by y. So that is essentially the same formula. Yeah, and so so combining all of these, we have a formula for the gradient that's given by minus x hat plus y hat plus z hat minus of that whole thing divided by x squared plus y squared plus z squared to the power of 3 by 2. Okay, so this is the gradient in Cartesian coordinates. Any question about this? Okay, if not, let us continue. We want to re-express this in polar coordinates. So first of all, psi in spherical polar coordinates is simply 1 upon r. Yeah, and the gradient of psi is given by minus r vector divided by r cubed. Sorry, r to the power of, what did I do? Yeah, simply r cubed. Yeah. So that can, of course, be simplified, and you can write it as minus r hat upon r squared. So this is basically part A. I hope you have been able to handle this. Okay, this is, of course, a very important example. There's a reason we are discussing it. It's going to come up again and again in various parts of physics and mathematics. So let us just describe it in words and through a figure. So first of all, the gradient points radially inward. Yeah, that is simply from the formula. Points radially inward There are other reasons for that also. It's also the magnitude falls off as the inverse square of distance from the origin. So this would be saying inverse radially inverse because there's a minus sign. We could have anticipated that basically because psi, what is the direction in which psi increases most rapidly? Could you advise me on that?
Yes, sir, that would be radially inward because psi is constant on a sphere, and it increases as the distance from the origin decreases.
Yes, indeed. So psi is constant on a sphere of centered at the origin, and then the size of psi decreases as you go out. So the direction of most rapid increase of psi is radially inverse. Yeah, so if I were to plot psi as a function of r, yeah, it's blowing up at the origin and going to 0, like 1 upon r. And this is 0. And therefore, using our principle that we explained a couple of classes ago, the gradient must point in the direction of most rapid increase of psi. Yeah, and therefore that is radially inverse. So we've explained the calculation using this idea. Now, let us, physically speaking, does anybody want to offer any physical system where this vector field arises? Want to
So
have
charges
some,
and
yes?
gravitation, electrostatics and gravitation.
Yeah, very correct. Yes, so that was Kaustubh as well as somebody else, I think. Yeah, so indeed, this
luminosity of a point source also.
Yes, indeed. Yeah. Yeah. So several of the problems that you mentioned, I mean, the gravity of a point mass or the gravitational force of a point mass would basically have this inverse square distance dependence and point radially inward. So also would the electrostatic force due to a charge, of course, depending on the sign of the charge, it may be radially inwards or outwards. I mean, if you have two charges, you're talking about like charges or unlike charges. Yeah, and you've also pointed out I mean, this similar thing comes up in sound and in water waves. Yeah, so there are many places where a point source leads to this kind of field. Okay, so that's nice. Now let us, to continue the story, let us plot the vector field. What's that going to look like? So first we need to comment on it. We notice that psi depends only on r, not on theta or phi. So we say that psi is, how do you want to describe it?
Symmetric.
Indeed, so it is spherically symmetric. Yeah, I mean, that is simply repeating what was said before, that the value of psi is constant on spheres, concentric spheres centered at the origin. And therefore, if you make a rotation of the space around this, about the center, the value of psi is not going to change at the point you are measuring it. And that is why we say it is spherically symmetric. That has, of course, a consequence for gradient of psi as well. So grad psi, we say that grad psi is, I mean, it points radially inward, and that dependence doesn't depend on your angular position around the center. Yeah, so we will say that grad psi is also spherically symmetric. Yeah. So a spherically symmetric field is one whose magnitude depends only on distance from the origin and which points either radially inward or outward. Okay, so this is the prototype of a spherically symmetric field. And therefore, if we want to visualize it, of course, you can visualize it in 3 dimensions. If my head is the origin, then the field basically points towards my head from all directions. But to plot it in a paper, maybe it's helpful to choose some plane. So if we choose, say, the XY plane, then let us see what gradient of psi was. Grad psi from my formula in the XY plane, we put z equal to 0. Yeah. Then what is it? It is simply minus x hat plus y hat over x squared plus y squared plus z squared. Z is 0 to the power of 3 by 2. Okay, so of course this we can write in plane polar coordinates as minus r hat by r squared, essentially what we had before in spherical polars. So this field is relatively easy to draw. It points radially inwards. So we start, and it's larger when you're closer to the origin. So I'll draw a long arrow here. Yeah, and then as I go out, I'll draw shorter arrows. Yeah, you can do the same. And as I go further out, the arrows are going to get even smaller. So I'm trying to do that over here. I hope you get the idea. Any question about this?
Yes, for some reason I thought that the way you represent a vector field is that okay, if the magnitude is greater, then you just around say a curve, then you just draw it with a greater density, like you draw more arrows on that particular curve, and if it's not that great, then you draw it spaced out.
Sure, that is an excellent way to represent a vector field, so that it's the magnitude is represented with the density of arrows rather than the length of arrows. This is a fine way to go, yeah, that would be acceptable. So who offered that suggestion?
Anhad.
Anhad, yeah, Chaturvedi, was it?
Yeah.
Yeah, okay. So yeah, that is definitely acceptable. And you can see that here too. I mean, in my picture, if I focus on a place near the origin, there are many more arrows, whereas if I go a little farther out, there are fewer arrows over there. So the density is a lot more near the origin than elsewhere. Yeah, so that's a very fine way to go. Any other suggestions? Okay. If not, let us proceed further. I think that takes care of, okay, the choice of plane doesn't matter because the field is spherically symmetric, so the orientation of the plane doesn't matter. Yeah, the vector field doesn't depend on theta and phi. It points purely radially. So no matter which plane you pick, it will point radially inwards on that plane. In particular, the vector field always points along the plane chosen. It doesn't point off the plane or obliquely. Yeah, so it's a special feature of this vector field. It's not always the case. So I want to note that vector field grad psi points along any plane through the origin. Yeah, so in other words, in this formula, there was no z component once we went to the xy plane. Is that understood?
This is because the vector field points radially inwards.
Yes, Nirja. Yeah. It is because the vector field points radially inwards. So if you choose any plane through the origin, it will point radially inwards on that plane. It won't have any component flying off that plane. Indeed. Is that all right?
Yes.
Okay, good. Fine. So I think we can now move to the second problem, unless there are any further questions here. So just to give a physical terminology, up to some physical constants in the context of gravity, what would psi be called? Do you want to offer a name?
So when we're comparing it with electrostatics, it's electric potential.
Yeah, so let's
Gravitational
call this the
potential.
Newtonian. Indeed. So this is Kaustubh and others have said this is the Newtonian gravitational potential. Yeah, so that's what it is. I mean, if you're talking electrostatics, there will be the electrostatic potential. Newton's gravitational potential, and grad psi, well, up to some constant factors, would then be called the gravitational force. Force field due to a, let's write it here, due to a point mass at the origin. So that's what it is. It's the Newtonian gravitational field. Okay, any further ideas about this?
Or we can say that it is line charge electric field psi.
Sorry, first, who spoke?
So Shantanu.
Shantanu, is it? I didn't hear the name. Sorry, please say that again.
So name or a sentence that I have to.
I'm sorry, I didn't catch what you said. You said something about electric field line or something. Did I hear you properly?
Yes, sir. I was saying that we can compare psi with a line charge electric field.
Okay. Well, okay. That is not quite the case. See, if it's a line charge, that is charged not at a point, but along a line, then the resulting electric field or electric force field is only cylindrically symmetric and not spherically symmetric. So things are a little bit different. Of course, if you concentrate on a plane that is perpendicular to the line charge, then you will still have circular symmetry. But I would like to make a distinction. The situation here is somewhat different. Do you follow what I'm saying? The symmetry of the problem is really different.
Yes, sir. Yes.
Yeah, yeah, but it's a good point. Spherical as opposed to cylindrical symmetry. But this, in that case, the choice of plane does matter. If you choose a different plane, the direction of the force field will not be, would not first of all be tangent to the plane, and yeah, the situation is going to be different. Precisely because you don't have spherical symmetry. You only have cylindrical symmetry. So this is a point charge, and this is a line charge. Okay, any more nice comments? But I didn't catch the name of who told us about this line charge. I missed the name. Could you please identify yourself?
Sir Shantanu Bray.
Okay, Shantanu, thank you very much. All right, so let us now go to question 2. Yeah, so here I will just read it out quickly. Consider an idealized state rigid wire. Okay, so you have anticipated the second question, Shantanu. So we are considering a straight rigid wire of length L, of it infinitesimal thickness, basically zero thickness, fixed length. It's a rigid wire. Yeah, and it's free to move in the seminar hall of CMI. And the question is, how many degrees of freedom? Okay, so all right, so let us answer this question in 2 steps. We will use our strategy like we did in the class last time of choosing a marked point on the wire. So you are free to choose any point. Let me just for argument's sake choose the left-hand point, one end point. Yeah, and mark a dot of black ink or something over there. And then we can locate this one end of wire can be located anywhere. Yeah, and so we say that there are 3 translational degrees of freedom to locate the the endpoint. Okay, so those can be chosen as the XYZ Cartesian coordinates of that endpoint. Okay, so I hope you are comfortable with that. So having fixed the location of this endpoint, the marked point, you will notice that there are many possible ways in which we can orient the rod or wire. And I'm drawing a few of them here. The wire need not lie on any fixed plane. It can point in any direction in 3-dimensional space. Yeah, so we need to enumerate those possibilities. And many of you have done that nicely. I want to clarify something here because I think there is also some confusion with some of you. So please tell me, now I would call the remaining degrees of freedom by a certain name. Please offer the name.
So rotational degree.
Yeah, so rotational degrees of freedom. Yeah, I mean, basically the freedom to rotate the wire about that fixed point in 3-dimensional space. And the question is, how many degrees of freedom remain in that process? Yeah, and the answer to that question, many of you have figured out that there are 2 such degrees of freedom. And how do we understand that? Well, the point is, let's choose the other end of the wire. The other end of the wire can lie at any point, at any point on a sphere of radius L. Okay, I hope you will see this is L, so it can lie at any point on a sphere of radius L centered at the marked point. Okay, so and now the question is, what is the dimension of the surface of a sphere, or how many coordinates do you need to specify a point on a sphere? So we need 2 coordinates to specify a point on the surface of a sphere. Yeah, and these 2 coordinates could be the polar and azimuthal angle in spherical polar coordinates, for instance. All right. So combining the results so far, I mean, the final answer is that we have 3 translational degrees of freedom and 2 rotational degrees of freedom. That's a nice way of splitting them. So a total of 5 degrees of freedom, okay, for this system.
Could you please tell me what you mean by the word degrees of freedom?
Yeah, so degrees of freedom are how many real coordinates or how many real variables are needed to uniquely specify the location of all points in your system. Okay,
So does,
yeah, go ahead.
so does infinite line has a in a 3D space would have 4 degrees of freedom or 5? Because if we move it along the line's axis, then the points would move, but the line would remain same, right?
Okay, so you're considering an infinite line, is that right? Rather than a finite segment?
Yes.
An infinite segment. Okay, well, okay, this is somewhat of a mathematical idealization, but let me take a moment to think about that. Look, see, even if it's an infinite line, we are still free to put paint at some point on that line and mark a point there. And we are free to, as you said, we are free to slide the rod along its length.
Yes, sir.
Yeah, so at first glance, and when we do that, the points in the line are actually moving. Yeah, I mean, when you do that, they change their location. They go to a new location. So if you don't specify where the new locations are, you're losing some information. So I would say that the translations along the length of the wire are also degrees of freedom, even though it is infinitely long.
So basically, there's a map from R cube to R cube, which preserves the lengths and the angles, and you are just trying to find out that what are the minimum number of things it generate that is that what you do?
Okay, you are partly correct. See, yes, you are correct. Yeah, so we are correct. I am taking my, there is some place where the rod is located, but we want to, and it is oriented in a certain way, and we want to bring a rod to that place, and we're asking how many operations are we supposed to do. You can take that viewpoint, and it is correct. You would need to do 3 operations of moving the center of the rod to the desired resting place, followed by 2 rotations, 2 independent rotations to orient it correctly. And that those 2 motions are rigid motions of Euclidean space, namely translations and rotations. So in that sense, you are correct. Is that decent? Who spoke, by the way? Anhad. Okay. Are you satisfied?
Yeah. Yes, I'm
Okay.
satisfied.
Okay, thank you. Yeah, so I know that this concept is a little bit confusing at first, but I hope you're able to understand. I mean, even if it's an infinite wire, I mean, you can imagine there's a bunch of masses along the wire. If you want to push the wire along its length, you will need to expend some energy. So that's also a degree of freedom. I mean, I'm just giving a very rough physical idea for this, but we cannot ignore translations along the length of the wire. On the other hand, spinning the wire about the axis is not a degree of freedom here because it is infinitesimally thin. Okay, so that the locations of the particles in the wire do not change when I spin the wire about its axis. Okay, this is a very important point, and I think many of you have got it. So no degree of freedom associated to rotating the wire about its length. Yeah, about its axis. So if I have a wire like this and I rotate it about its axis, I don't change its configuration. I don't change the locations of any of the constituent particles. Yeah, so such a rotation does not relocate any particle in the slender wire. Okay, and so if you have not changed the locations of any of the particles, you have not invoked a degree of freedom. Okay, any question about this?
Sir, zero thickness, what is that required, zero thickness?
No, if thickness was not 0, but it was a pipe of non-zero thickness, then you have an extra degree of freedom beyond the 5 we have talked about, corresponding to spinning the pipe about its axis. Because when you do that, point here will move there, point here will move there, and so on. And okay, very good. Okay, so, but yeah, that's very pertinent. These are really 2 different systems. I mean, a rigid body of 0 thickness and a rigid body of non-zero thickness. They have different degrees of freedom, and their physics are different. In particular, there can be a rotational energy associated with such a rotation, whereas here there is no such rotational energy if it's infinitesimally thin. Okay. Any further questions about this nice little problem?
So suppose we enumerate the degrees of freedom as x, y, z, theta, phi, where x, y, z are like normal Euclidean coordinates, and then like theta and phi as spherical polar coordinates. Then like will we be getting mark? If you don't explicitly mention that there are three translational degrees and
Yeah, that's fine. Yeah, as long as you tell us what they are, you don't need to use the terms translational and rotational. That's acceptable. Yeah. But
Okay.
going forward, I would like you to use that terminology. It is certainly very physically very revealing to use that terminology. And as I think Anand pointed out, using that terminology also connects it to the set of Euclidean motions of the Euclidean space, namely rotations and translations. Okay. Yeah. So now let us go to the third problem. Any further questions? Okay, if not, let's. So this concerns Newton's first law. So the statement is that so particle is isolated. So isolating a particle is a way of eliminating all forces. So no forces. It is not subject to any force. However, if observer who is observing this particle, so observer A finds that it accelerates. Okay, so that is the statement with respect to A's frame. And the question is, on the basis of Newton's first law, tell whether A's frame is inertial or not. Okay, so now, first of all, the particle is isolated, so Newton's first law applies, because Newton's first law is a statement about isolated particles. Okay. Yeah, so let us make the assumption, let us suppose frame A's frame is inertial. So let us suppose A's frame is inertial and deduce some consequence. Well, if A's frame is inertial and we know that there are no forces, then Newton's first law implies that particle must have constant velocity. Okay, so that is a direct consequence of Newton's first law. So this is NFL stands for Newton's first law. I hope you will accept that abbreviation. Yeah, there are other things that it also stands for in sports. Anyway, so but then the statement is that it's accelerating. So this is a contradiction. Yeah, it contradicts the statement that it accelerates. So the assumption must have been wrong. So the assumption of A's frame being inertial must be wrong. So we will conclude that A's frame must be non-inertial. Okay, so that is the idea concerning this problem. Please tell me if you have any questions about this.
So description of this length should be enough for this problem, right?
Yes, yes. Couple of sentences, 2-3 sentences of this sort is adequate. Yeah. I mean, if you have argued a little bit more, it's okay, but this is definitely adequate. Of course, the assumption, the logic has to be clearly presented. Okay, any other question? Okay, if not, let us proceed to the next question, which is 4. Yeah, so 3 is basically concerning acceleration without force. Yeah, So, I mean, just to give a slogan, what we have discussed in problem 3 is a observer noticing acceleration without any force. And if what we have concluded is that if that happens, that the observer's frame must have been non-inertial. So that is the conclusion. We will meet this later on also. Yeah, so anyway, that is as much as I want to say right now. So acceleration without force implies non-inertial frame. Okay, so I have summarized our discovery in these 2 lines.
No, so not acceleration with force.
I'm sorry.
Not acceleration without force implies non-inertial frame. Also, if no acceleration, even if force is there and no acceleration, there is also non-inertial, right?
Okay, you are asking a different question. I think it is basically related to the 4th problem. Just hold on. Okay, okay, that was on-con, am I right? So could you please repeat? You are considering, please repeat your observation or question.
No, in that if I observe that there is the 4th question, yeah, actually it is literally the 4th question.
Okay, let's finish the 4th question and then maybe you can revise your point. Let's look at the 4th question. So the 4th question concerns sort of the reverse of this statement, namely, we are told there is a force, but there is no acceleration observed. Yeah, so let me just start with the slogan. Force, but no acceleration. So that is what the 4th problem concerns. So, but let us be a bit more specific about it. So we are told that a particle is subject to a net force. By net force, I mean the vector sum of the forces is not 0. Okay, so when I say net force, the vector sum of all individual forces is non-zero. Okay. Okay. Then, but what is found is that an observer finds that particle does not move. Of course, the observer is observing this particle from some time onwards. What happened before that? Did it start at rest? Did it not start at rest? Is not known to this observer, and it is not relevant to the question right now. Okay, so the observer, since the time he looked at it or she looked at it, finds the particle does not move. Okay. So the question in part A is to say, based on Newton's first law, and Newton's first law, that is based on Newton's first law, what can be deduced about the observer's frame, whether it is inertial or non-inertial. Okay, so first of all, let us just recall what Newton's first law was saying. Newton's first law said that for any isolated particle, there is a frame in which it moves in moves at constant velocity. Okay, so this was the content of Newton's first law. Newton's first law says that free particles, for a free particle, there exists a frame in which it moves at constant velocity. Okay, so this was, so this E written laterally inverted is means there exists. Okay, so on the face of it, or at least as stated, Newton's first law only concerns free particles, not particles subject to forces. So a direct application to a problem where there is a force would not be under the purview of Newton's first law. So basically, Newton's first law does not apply to a situation where the particle is subject to a net force. Okay, so for that reason, we would say that we cannot conclude I mean, since Newton's first law does not apply, or rather it applies only to free particles. The Newton's first law applies only to free particles, so we cannot conclude whether the frame is inertial or non-inertial based only on Newton's first law. Okay, so this is what, so there is no, this question is not answerable if all you have is access to Newton's first law. Any question about that? Okay, if not, yes.
Do we need the first law if we have the second?
The situation changes if we have the second law, indeed. So the first law is only half the story.
Doesn't the second law contain the first law?
Okay, the second law, in a sense, I wouldn't say it contains the first law, because then we would even eliminate it, and Newton would not have given two laws. Yeah, the content of the first law is it's a statement of existence, okay, that there is an inertial frame. That is a very deep statement, that there is such a frame. Second law doesn't say that there is such a frame. Second law says that if you are working in an inertial frame and there is a force F, then the particle will accelerate in this manner. Okay, so
can that be also be used as a description of the inertial frame? Like if F is equal to ma holes in that particular frame, then it's an inertial.
Right. Okay, you're saying that okay, maybe I'll try to be more specific about this. You are saying that the second law, in a sense, can be used to define an inertial frame. Okay, I'm a little bit hesitant to do that. Let me think over that once more. I mean, you are right that if F is 0, then the solution of Newton's second law equation of motion does tell you that the velocity is a constant. So to that extent, it is very closely related. Yeah, but let me just try to clarify that. That is Anhad, am I right?
Yes.
Okay. Yeah, but I would, before I come back on this, for now, I would like to view the first law as telling you that inertial frames exist. And without that, we cannot proceed to other discussions. I think that is the crux of the matter. You need to know that such a frame exists. And then you can, of course, discuss as to how a particle will move subject to forces in such a frame. Okay, anyway, you can just see whether what I said makes sense. Yeah. Sort of Newton's second law is built around working in an inertial frame, but whether that inertial frame exists or not is still an open question, and that is settled by the first law. This is my, at least in a quick way, this is my what I would like to advocate. Is Anhad with me on that? Okay. Okay, if I can improve on that statement, I will. Yeah, please.
So does it mean that the second law completes the first law?
No, the second law tells you more. I mean, the first law has only very limited purview. It only deals with free particles, right? The first law only says that if a particle is free, then there is a frame called an inertial frame in which it will move in a straight line at constant speed. Yeah, so it doesn't tell you anything about what would happen if there is a force and so on. And in that sense, Newton's second law extends the first law to a larger class of physical situations, namely where there are forces present. So in that sense, indeed, Newton's second law completes the first law. But I hesitate to use the word complete, because what does it mean to complete? Can there be no other law? Can there be no other additional information? And it turns out there is other information that is needed, that is independent of these two. Yeah. So I would prefer to use the word extends, or is additional piece of information about the nature of physical phenomena. Okay, that was Nirjal. Is that all right?
Yes, sir.
Okay, any further questions about this? Okay, then the last part, which is B, that is, we have Newton's second law also available at our disposal. So let me just summarize Newton's second law over here. It would say that in an inertial frame, particle motion is governed by mass times acceleration is equal to the force. Okay, so I mean, I can say this in a better way perhaps, but this is the essential statement, that in an inertial frame, the mass times the acceleration is equal to the force. Okay, so now if we apply this to the particle that we were considering, namely one where there is a net force, so we are told that F is not equal to 0. So by then, if frame is inertial, then acceleration must also be non-zero. I mean, we are assuming the mass is not 0. Okay, so we are assuming the particle is not massless. So within non-relativistic mechanics, we are only considering massive particles. I will say more about that. So if the frame was inertial, then the acceleration must be non-zero. But since the person has observed the particle to not move, but we are told that the acceleration is 0, so the assumption of the frame being inertial must be wrong. Okay, so in other words, the frame must have been non-inertial. Okay, so okay, so that is as far as this part B is concerned. I have a feeling somebody's microphone is on and we are hearing some background noise.
Ryan.
Okay, so if you could just mute your microphone unless you're of course speaking. Yeah.
Sorry, sir, I did not notice.
Okay, thanks. Okay, so any further questions about the problem set?
Sir,
yes.
If Newton's second law is not contained within the first one, so Newton's first law is an expression of there exists some inertial frame, and Newton's second law develops on that.
Indeed.
Indeed. So I know they're different, but what is the use of their difference? Why did not Newton make it in one law? Did he he would not have made it in one law? Are they separate because you cannot make them same?
Okay, I will. Okay, see, the answer to that question is partly coming up in the succeeding discussion. This separation between the laws has a lot of utility. Yeah, I mean, it's a question of how you present the axioms or the assumptions or the postulates. Yeah, so there are many ways to do it. As I mentioned in an earlier work by Newton before his Principia Naturalis Mathematica. So he had another manuscript called De Motu Corporum something. Yeah, in that he had several more laws, in fact. and he combined some of those into the three laws as we currently know it. So there are different ways of presenting these things. I will say, with the benefit of hindsight, that there is something to be said for separating Newton's first and second laws. I mean, if you want to combine them, you will have a longer statement. I'm not sure how. I mean, yeah, you might as well keep them separate if you wanted. I believe they are logically one is a development over the other. But you will see that when we extend this to other contexts, it is very useful to know whether Newton's first law continues to hold or doesn't hold. Yeah. Suppose we are extending this discussion of mechanics to relativistic mechanics. Then we can ask how is each of these laws modified, or whether one is modified and the other is not modified. In that context, it is very helpful to have this distinction between the two laws. Yeah, and I will also discuss it in the context of Galileo's relativity principle. So there too, having this distinction is quite helpful.
Sir, I'm only asking because usually, as far as I've seen, axioms are usually quite disjoint. They're not very related to each other, usually. That's why I'm asking.
Okay.
I mean, that is my final comment. That was not a question.
Okay. Fine. Yeah, there may be systems where the axioms are totally disconnected or something, but here the second law makes use of some things that are developed in the first law, namely the existence of an inertial frame. So in that way, yeah, it is a building a first floor and then kind of the superstructure. Okay. Yeah. Okay. So any further questions? Yeah. Anyway, I believe if you have worked through this problem set carefully, you would have learned a lot of very valuable things. And I do appreciate all 43 of you who have submitted these answers. And you are definitely richer for it. Okay, so with that, let me go back to our discussion from last time. I want to return to where we were. Okay, I wanted to mention one example, which I should have said last time. I somehow slipped my mind. There was this discussion of evidence for the Earth being an inertial frame. Yeah, one kind of, I mean, one has to do experiments to find out, right? So it's not that easy just to say, but I wanted to mention this example. So it is possible. So I stated that the Earth, to some approximation, can be regarded as an inertial frame for certain purposes. Yeah, for some purposes such as the motion of golf balls and such things, or the rolling of a ping pong ball on a table. Yeah, for these things, it can be.
I cannot see the screen.
Oh, I'm sorry. What happened to the screen? Okay. Let's see. Am I?
Sir, but I can see the screen.
Oh, you can see. One person can see, another cannot see. All right. So,
no, sir, it was visible.
It was visible. Okay, I am reassured. So, on-con, please do check whether you can see the screen now. And please tell me if any of you are not able to see the shares.
I'm leaving and joining.
Okay, you're welcome back. Are you going to come through the same door or a different door? You can decide. Okay, so it is possible. Yeah, so as I was saying, the Earth's frame can be regarded as inertial for certain purposes. I mean, to a reasonable approximation. It's always in that context. Yeah, but if you are studying phenomena that are very sensitive to the rotation of the Earth, or celestial phenomena like the motion of planets and so on, then it may not be reasonable to take the Earth's frame as inertial. Okay, so one needs to be clear about which phenomena one is focusing on. Yeah, so I mean, physics is like that. We need to tell. Yes, please.
Sir, the LIGO experiment, does it take into account the non-inertial frame of reference or what?
Yes, yeah, they do account for these things. Yes, yeah. The accuracy they have achieved is enormous, so they have to take into account all of these things. Okay. Now, I wanted to mention, of course, the context is somewhat different, and that discussion requires a dedicated effort. But yeah, it certainly takes account of the motion of the Earth and so on. Okay, now it is possible to reduce the effects of gravity and friction in some cases of motion of objects on the Earth, so that one can contemplate a particle which is essentially free for certain purposes. So let me give a simple example of that, a limited example. Okay, so here we consider the horizontal motion of a ball on a table tennis table placed in a tennis court. Okay, so we were talking about a tennis court. So let us take our tennis court, and in that court we place a ping pong table, and on that table, I mean, it's placed horizontally with respect to the Earth, and we consider the horizontal motion of a ball on that table. Okay, now what do we find experimentally? Well, first, a ball that starts out at rest is by and large seen to remain at rest. Okay, there may be some wind which may cause it to move. Of course, you will shut the windows or put it in some box and so on. So you need to eliminate those effects. Or if the table is not really horizontal, it's a bit inclined, it may start rolling, but you have to try to eliminate these effects to the extent possible. Yeah, so but by and large, the observation is that a ball that starts out at rest remains at rest. So that is one of the parts in Newton's first law. The second one is to check what happens to a ball that starts out rolling. So suppose a ping pong ball starts out rolling on the table in some direction. What we see is that it continues to roll in the same direction. Okay, that is what our general observation is, though it is seen to slow down. Yeah, somewhat slow down. It may roll for quite a while actually, because ping pong balls have very little friction with the rolling friction. So we attribute this to the friction with the surface. Now the magnitude of this frictional effect, of course, depends on the weight of the ball. I mean, there are ways to model this frictional force. We can talk about that later. It does depend on the weight of the ball, but so that weight of the ball depends on gravity, right? So gravity does play a role, but we may sort of remove this effect as much as possible by polishing the surface and the ball, and thereby reduce the effect of friction. The effect of gravity, I mean, gravity points downwards. So in horizontal motion, it plays very little role. It plays an indirect role through controlling the magnitude of the frictional force, right? But even that can be made essentially arbitrarily small. Yeah. So in other words, what we find is that the ball maintains its velocity for a long time. Okay? So based on this evidence, we would arrive at a body, namely a ball, that is essentially free. That is, it is not subject to these forces like gravity and friction, insofar as its horizontal motion is concerned. Okay. So basically, this is the kind of thing you have to do. You need to convince yourself and your co-workers and colleagues and friends that you are studying a free particle. Okay, so and that is a matter of debate and trying things out and improving and so on. It is not a self-evident fact that, okay, this is a free particle. You need to check. And others need to repeat the experiment and reproduce your results. Yeah, all this needs to be done. So as far as the horizontal motion of a ball on a ping pong table is concerned, we are reasonably convinced that it is free, and not only that, it is observed to proceed in rectilinear fashion at constant velocity. Yeah. So this uniform motion is evidence in favor of the inertial nature of the frame fixed to the Earth. Okay, at least for this limited class of motion, namely horizontal motion. Okay, so in other words, we have basically sort of cancelled out the effect of gravity. Gravity points downwards, but the table exerts a normal reaction force on the ball, and so that of balances gravity so that there is no motion in the vertical direction. So we have done the sort of thing I suggested last time, that we have used a clever way of cancelling out gravity. You could cancel it out through other procedures, maybe through electric forces and so on, but here we have used a more elementary method. Okay. Any question about that?
Sir, I have a question. One thing, the Newton's first law says that there exists an inertial frame such that that the rest of the statement. But I'm asking that exactly. I mean, can you please elaborate on what does this mean? There exists an inertial frame. I mean, where is this inertial frame? I'm pretty confused on this.
Okay. That inertial frame is a triad of axes. All right. So if I have my table, my ping pong table, where is that frame? It is right here. It is my 3 fingers, which are fixed to the corner of my ping pong table, oriented in a specific manner. Okay. So maybe 2 of the axes along the 2 edges of the table, and the 3rd axis is pointing vertically upwards. So that is my frame. Yeah, and by frame I mean a choice of 3 mutually perpendicular axes, of course extending out, and a choice of time. All right, so there is some clock that we keep there. So these things together are called a frame. Yeah, so it's a very concrete setup.
Okay. It can be anywhere, right? Constructed. I mean.
Yeah. You can place it somewhere else in another corner or a little bit elevated. Yeah, you're not obliged to make the choice I made. And that comes to a very deep principle of physics, which is coming up shortly. Yeah, about the homogeneity of space. That is, we can move our frame, all right, and the results of mechanical experiments do not change. Yeah, so the choice of frame is not unique. The choice of inertial frame is not unique. Okay, so I will say more about that shortly.
Sir, I have a question.
Yes, please. Sorry, who is speaking?
Sir, Shantanu.
Okay, Shantanu Oberoi. Yes, please go ahead.
Sir, what kind of force is friction? Is it a gravitational, electromagnetic, or nuclear?
It's an electromagnetic force. Yeah, friction is by and large an electromagnetic force. So, I mean, at a microscopic level. We don't need to know anything about electromagnetism to talk about friction. We can talk about it as an effective force that my finger feels when I try to roll it on my arm. Yeah, it's a force that tends to point in a direction opposite to the direction of motion and tends to slow things down. All right, so that is the effective description. But microscopically, it is arising because of electric forces between molecules in the moving body and the body at rest, yeah, between the relative motion of those 2 bodies. Yeah, so it is electric in origin. It is not gravitational in origin, and it is not nuclear. Nuclear effects are not important here. It's largely electromagnetic. Is that okay, Shantanu?
Yes, sir.
All right. Okay, so let us continue then. Okay, we are nearly out of time, but I did want to begin discussing Newton's 2nd law in a little bit more detail. Let me just start that. Yeah, so let me just say that the departure from rest or uniform motion along a straight line in an inertial frame is caused by forces. Okay, so this is a general idea. And for example, tugging at a string that is attached to a ball exerts a force on the ball, okay, and makes it accelerate. So this is the observation, and Newton's 2nd law is a sort of a mathematical statement of what they observe happening. So I mean, I haven't said very precisely what a force is, but a force is sort of operationally defined. It is what is making the ball accelerate. It is my pushing the ball. It is my tugging the string. Okay, so we are thinking of a force as arising through such processes. So forces typically arise from interactions between objects. So that's very important to bear in mind. Forces arise between the interaction between my hand and the ball, or my arm and the string, yeah, or the earth and this water bottle, and so on. Okay, so forces have that character. They're typically between objects. So the earth exerts a force on a ball. yeah, that is dropped, making it accelerate downwards. Okay, so this is our observation and idea. Okay, so let me go a little bit further. Yeah, so see, unlike acceleration or position and velocity, which were defined purely through some geometric procedure using trajectories and tangent vectors and so on, and through calculus procedures of calculating derivatives, the force doesn't arise in that manner. The force is some separate physical concept. We are going to relate the two now. So just a moment. So Newton's second law says that in any inertial frame, okay, so notice for the very statement assumes that an inertial frame exists. Yeah, so that this is not an empty statement. So it is in that sense that Newton's second law is based on Newton's first law. Yeah, without Newton's first law, the statement itself will not make sense. Says that in an inertial frame, the rate of change of momentum, which is written P dot, is equal to the impressed force. Okay? So the force on the particle results in so the rate of change of momentum is equal to the impressed force. In particular, the rate of change of momentum is in the direction in which the force acts. Okay, so let us write this as a formula. So for a single particle of mass m, let us take that specific case. The acceleration a vector is given by the second derivative of the position vector, or in other words, equal to p dot upon m. Because p was itself mass times velocity, so p dot is mass times acceleration. So when I say the rate of change of momentum, I simply mean ma double dot. Okay, so that is, they are no different for a particle. So the trajectory r of t due to the force F, so this is the statement of Newton's second law, is determined by the equation. It's called the equation of motion. And it is the following equation: mr double dot equal to F. So both sides are forces. F is a force and acceleration is a force, or written in terms of momentum, it's P dot equal to F. Okay, so this is the statement of Newton's second law for a point particle. Here we have introduced a object, a quantity called m, which is more precisely called the inertial mass. I will explain the reason for that name. So m is the inertial mass of the particle. It is postulated to be independent of time. So the mass of a particle is independent of time, and it has certain properties. I will discuss those properties, but I think that needs to be done next time. I'm out of time now. So any questions about what we have said so far today?
Sir, in the second part of the fourth problem in the assignment, sir,
Yes.
I have written that m is the mass basically while explaining the terms in the equation. So,
yeah.
like, is it fine? It's actually inertial mass.
Yeah, it's okay to call it mass. See, only when we want to be very precise, we can say like inertial mass. If you simply call it mass, that is fine. Yeah. But I will make the point as to what we mean by inertial mass, what is the other type of mass, and so on. I will describe that, but right now it doesn't matter. Okay. Any other questions? If not, we will halt here and reconvene on Thursday. So I think that is all I have for now. So have a good afternoon and other classes.